Section. Introduction. In this study, we're exploring the idea that increasing the depth of a transformer language model, meaning the number of layers it has, can improve its ability to understand and generate sentences it hasn't encountered before. This concept is known as compositional generalization. While transformers have been successful in many areas, they often struggle with tasks that require this kind of generalization. Our hypothesis is based on both theoretical and experimental work. Theoretical work has shown that adding more layers to a neural network can increase its expressive capacity, and experimental work suggests that deeper models may be better at compositional generalization. However, there's a catch. As we add more layers to a model, we also increase its size, meaning the number of parameters it has. And since the performance of language models is strongly linked to their size, we need to find a way to separate the effects of depth and size. To do this, we created models with the same total number of parameters but different depths. We achieved this by reducing the model's feed-forward dimension as we added depth. We then trained these models on language modeling and fine-tuned them on 4 tasks that require compositional generalization. We also considered other factors that could affect generalization, such as the model's performance during pre-training or fine-tuning. To account for these factors, we also looked at the effect of depth on language modeling performance and in distribution loss. Our findings showed that, in general, deeper models performed better on tasks requiring compositional generalization. However, the benefits of adding more layers diminished quickly as models got deeper. To create deeper models without increasing the total number of parameters, we had to make them narrower. We did this by reducing the size of the feed-forward dimension, the size of the residual stream, or the size of the attention outputs. We kept the attention mechanism the same across all models to avoid confounding the effects of depth and the capacity of the model's self-attention mechanism. We also derived a formula to calculate how much the size of the feed-forward dimension needed to change when we added or removed layers. This allowed us to create models with nearly the same total parameter count, even though they had different depths. In some cases, this resulted in models where the feed-forward ratio was greater than 1, meaning the size of the model was greater than the size of the feed-forward dimension. We explored the implications of this in our study. Section Summary. In this paper, the authors investigate the impact of increasing the depth of transformer language models on their ability to generalize compositionally. They find that deeper models generally have lower perplexity and display better compositional generalization, with most of the benefit of depth accruing from the first few layers. The authors construct models with equal numbers of parameters but differing depths by reducing the feed-forward dimension, and they rule out confounding factors by keeping the attention mechanism identical across models. Section. Language modeling. We're going to talk about language modeling using the Colossal Clean Crawled Corpus, or C4 for short. This corpus was created by filtering data from a dataset of web files known as the Common Crawl. We use a context size of 1024 tokens and a batch size of 128 sequences, which is roughly equivalent to 131,000 tokens. We train each model for one step, resulting in a total training dataset of about 131,000 tokens. Next, we'll discuss compositional generalization. In these datasets, models are tested on a distribution that contains new combinations of pieces, each of which has been seen independently during training. We fine-tune our pre-trained models on the training portion of the dataset for 10,000 steps, measuring the accuracy every 250 steps. We noticed that the validation loss continued to decrease throughout training runs on each dataset, so we report values from the end of each fine-tuning run without stopping early. We use 4 compositional generalization datasets. The first one, COGS, is a semantic parsing dataset designed to test compositional generalization. It consists of natural language sentences paired with formal semantic representations. The second one, variable-free COGS or COGS-VF, is a simplified version of COGS where the semantic representations do not use numbered variables. This simplification reduces the computational cost of training by making sequences shorter. The third dataset, GeoQuery, contains natural language questions about U.S. geography paired with SQL-style database queries. The fourth dataset, English passivization, consists of English active voice sentences paired with their passive voice counterparts. This dataset is designed to test whether models use shallow, positional heuristics or syntactically sensible ones. We found that the depth of a model significantly impacts its performance. At the shallow end of the spectrum, increasing model depth results in a dramatic improvement in perplexity. In the extreme case, the perplexity of a single-layer model can be nearly twice that of the optimal model in the class. Moreover, as the number of parameters increases, the disparity between the worse, shallower models and the better, deeper models also increases. While deeper models generally perform better than shallower ones, the increase in performance that comes from adding layers diminishes rapidly as models become deeper. The performance difference between one-layer and two-layer models is dramatic across all size classes. Moving from 2 to 4 layers results in a much more modest performance improvement. We also note that as models get larger, they are able to make productive use of increasingly more layers. However, at the deeper end of our scale, adding layers is not only unhelpful for performance, but begins to harm it. The point at which trading width for depth becomes harmful is not an absolute function of depth, since the optimal models from each size class have differing depths. However, comparing the relative performance of models within a size class to the feed-forward ratio shows that model performance begins to worsen once the feed-forward ratio becomes smaller than the model ratio. When this happens, the affine projection of the vectors from the model space into the feed-forward space becomes a non-injective map. In the next section, we analyze the weight matrices of the affine transforms in the feed-forward network of each layer and demonstrate that as the model ratio over the feed-forward ratio increases, the transforms become increasingly rank-deficient. Section Summary. The authors use the colossal clean-crawled corpus, C4, as their pre-training corpus, with a context size of 1024 tokens and a batch size of 128 sequences. They fine-tune their pre-trained models on 4 compositional generalization datasets, including COGS, COGS-VF, GeoQuery, and English passivization. They find that increasing model depth improves performance, but the performance gain diminishes rapidly as models become deeper. Additionally, adding too many layers can harm performance, indicating that there is an optimal depth for each model size. Section. Larger models are more robust to changes in the feed-forward ratio. We've discovered that larger models are more resilient to changes in the ratio of feed-forward networks to the size of their contextual embeddings. When we alter the size of the feed-forward network while keeping the model size constant, we get ratios that differ significantly from the standard ratio of 1 to 4. Smaller models are more sensitive to changes in this ratio, and the standard ratio may not be the best for them. In the 41-parameter size class, there's a small range of feed-forward ratios where the model's performance is almost as good as the best model in that class. As models get larger, this range expands to include models with larger feed-forward networks relative to their contextual embeddings. This suggests that larger models can afford to be wider in relation to their model size without significantly affecting their perplexity, a measure of their performance. We also found that when the ratio of model size to feed-forward network size is less than 1, the feed-forward ratio no longer predicts perplexity regardless of the model's size. To understand the effect of model depth on compositional generalization, we fine-tuned the models we had pre-trained on each of the compositional generalization benchmark datasets. We found that deeper models generally perform better. However, the effect of depth on compositional generalization varies across different tasks. For some tasks, most of the benefits of depth are gained by having only a few layers. After a certain number of layers, the generalization accuracy remains relatively constant as depth increases. This threshold varies by dataset. We also found that even deep models at the largest model size struggle to generalize structurally. The benefit of depth is largely limited to the easier lexical generalization. This suggests that the effect of depth saturates due to the existence of easier subsets of the datasets, and that increasing depth alone doesn't significantly improve the model's ability to learn the correct inductive bias for these structural tasks. Although deeper models generalize better than shallower models, our analysis shows that deeper models also achieve lower perplexity on their pre-training corpus than shallower models. Additionally, deeper models achieve lower loss on the fine-tuning tasks than shallower models. To determine whether depth directly improves generalization accuracy, we corrected for these potential confounds. We repeated our fine-tuning experiments using models that have equal perplexity within a size class. We found that even when fine-tuning from checkpoints of equal perplexity, deeper models still generalize better than shallower models. Next, we corrected for the fact that deeper models learn the in-distribution split of the compositional generalization tasks better than the shallower models do. We compared the generalization accuracies of models at points during fine-tuning when they have equal in-distribution loss. We found that even after adjusting for in-distribution performance, deeper models still achieve higher accuracies on the out-of-distribution generalization set than shallower models do. Section Summary. Larger models are more robust to changes in the feed-forward ratio, with smaller models being more sensitive to the specific value of the ratio. Deeper models tend to generalize better in compositional tasks, although the impact of depth on generalization accuracy varies across different datasets and tasks. The benefit of depth saturates quickly, with only a few layers providing most of the improvement, and the threshold depth for optimal performance differs depending on the dataset. Increasing depth alone does not substantially improve models' ability to learn the correct inductive bias for structural tasks. Deeper models also achieve lower validation perplexities and in-distribution loss, but even when these factors are corrected for, deeper models still generalize better than shallower models. Section: Compositionality. We've been looking into how well neural models can handle tasks that require a compositional understanding, such as interpreting simple command sequences or semantic parsing. Some researchers have tried to enhance this compositional behavior in models by using data augmentation, larger models, and changes in architecture. Our contribution to this field is to investigate a specific architectural change, increasing the depth of the model without changing its overall size. We're mainly focusing on models that are less deep but wider than the standard ones. Given that the model size is fixed within each class, this means that most of our models have smaller feed-forward ratios. As the size class increases, the differences between our models and the conventional ones become more pronounced. The exact number of parameters in our models may differ from others due to variations in the size of the vocabulary, embedding layers, and because we use decoder-only models rather than encoder-decoder models. However, the internal parameters of our base models are consistent with theirs. The depth of a model has been shown to have a significant impact. Theoretical work has shown that the expressive capacity of neural networks, especially transformer models, grows exponentially with depth. Empirical work also suggests that depth plays a crucial role in model performance. For tasks that require compositional generalization, reducing depth was found to be more harmful than reducing width. However, it's also been noted that even very deep networks with residual connections often only use shallow subnetworks of roughly constant depth. When controlling for model size, there are various decisions to be made. Some researchers have varied the number of layers with the contextual embedding dimension, which they link to the attention internal and feed-forward dimension at a standard ratio. They concluded that performance improvements are largely driven by increasing the total parameter count of models, and that language modeling perplexity is only weakly dependent on shape within reasonable limits. Due to computational constraints, the results we report represent a single pre-training and fine-tuning run for each condition. Multiple runs for each condition would decrease noise in the results, increase our confidence in the effect sizes we report, and allow us to quantify our uncertainty over them. An alternative approach to controlling for total size would be to construct universal transformers, where each model in a size class has a transformer layer with the same parameters repeated multiple times. This would allow for deeper models to have arbitrarily wide feed-forward networks, mitigating the impact of making models too narrow. We also consider models pre-trained on natural language data. For our specific choice of compositional generalization experiments, the presence of lexical items in both the pre-training corpus and the generalization datasets could potentially affect generalization performance. As a future area of interest, we suggest the hypothesis that including source code in the pre-training corpus could improve compositional generalization. Section Summary. In this section, the authors discuss the concept of compositionality in neural models and how it has been explored in previous work. They focus on increasing the depth of models without changing the total model size and compare them to standard architectures. The authors also discuss the impacts of depth on model performance and the need to control for model size when studying hyperparameter choices. They mention the limitations of their study due to compute constraints and propose alternative approaches to controlling for total size. Finally, they mention the effects of pre-training corpus on generalization performance and suggest including source code in the pre-training corpus as a potential improvement. Section: Fine-tuning versus in-context learning. We employ a method known as fine-tuning to adjust our pre-trained models for specific tasks that require understanding of compositionality. However, as the size of the model increases, fine-tuning becomes less practical due to its high computational cost and task-specific nature. On the other hand, in context learning, another method of model adaptation, only becomes dependable when used on a much larger scale than we can currently handle. Therefore, we haven't been able to investigate how the depth of the model affects its ability to accurately generalize in context learning. We suggest this as a potential area for future study.